comparative statics with small changes. Alternatively, we can use calculus to determine the effect of a small change as opposed to the discrete change we just used in one environmental variable, holding the other such variables constant. Until now, we have used calculus to examine how an argument of a demand function affects the quantity demanded, or how an argument of a supply function affects the quantity supplied. Now, however, we want to know how an environmental variable affects the equilibrium price and quantity that are determined by the intersection of the supply and demand curves. Our first step is to characterize the equilibrium values as functions of the relevant environmental variables. Suppose that we hold constant all the environmental variables that affect demand, so that the demand function is capital Q equals capital D of P, equation 2.9. The environmental variable A in the supply function changes, which causes the supply curve to shift. We write the supply function as capital Q equals capital S of P and A, equation 2.10. As before, we determine the equilibrium price by equating the quantities capital Q in equations 2.9 and 2.10. Capital D of P equals capital S of P and A, equation 2.11. Equation 2.11 is an example of an identity. As A changes, P changes, so that this equation continues to hold. The market remains in equilibrium. Thus, based on this equation, we can write the equilibrium price as an implicit function of the environmental variable P equals P of A. That is, we can write the equilibrium condition in equation 2.11 as capital D of P of A equals capital S of P of A and A, equation 2.12. We can characterize how the equilibrium price changes with A by differentiating the equilibrium condition, equation 2.12, with respect to A using the chain rule and the original equilibrium, superscript 10, which reads, the chain rule is a formula for the derivative of the composite of two functions such as f of g of x. According to this rule, df over dx equals open parentheses df over dg close parentheses open parentheses dg over dx close parentheses. See the calculus appendix at the end of the book. D, capital D of P of A over dP multiplied by dP over dA equals italics capital D capital S of P of A and A over italics capital D P multiplied by dP over dA plus italics capital D capital S of P of A and A over italics capital D A. Using algebra, we can rearrange equation 2.13 as dP over dA equals italics capital D capital S over italics capital D A over D capital D over dP minus italics capital D capital S over italics capital D P, equation 2.14, where we suppress the arguments of the functions for notational simplicity. Equation 2.14 shows the derivative of P of A with respect to A. We know that d capital D of dP is less than 0 because of the law of demand. If the supply curve is upward sloping, then italics capital D capital S over italics capital dP is positive, so the denominator of equation 2.14, d capital D over dP minus italics capital D capital S over italics capital dP, is negative. Thus, dP over dA has the composite sign as the numerator of equation 2.14. If italics capital D capital S over italics capital dA is negative, then dP over dA is positive. As A increases, the equilibrium price rises. If italics capital D capital S over italics capital dA is positive, an increase in A causes the equilibrium price to fall. By using either the demand function or the supply function, we can use this result concerning the effect of A on the equilibrium price to determine the effect of A on the equilibrium quantity. For example, we can rewrite the demand function equation 2.9 as capital Q equals capital D of P of A, equation 2.15. Differentiating the demand function equation 2.15 with respect to A using the chain rule, we find that D capital Q of D over dA equals D capital D over dP multiplied by dP over dA, equation 2.16. Because italics capital D over italics capital D P less than 0, by the law of demand, the sign of D capital Q over dA is the opposite of that of dP over dA. That is, as A increases, the equilibrium price moves in the opposite direction of the equilibrium quantity. In solved problem 2.1, we use the pork example to illustrate this type of analysis. Solved problem 2.1. How do the equilibrium price and quantity of pork vary as the price of hogs changes if the variables that affect demand are held constant at their typical values? Answer this comparative statics question using calculus. Hint, this problem is of the same form as the more general one we just analyzed. In the pork market, the environmental variable that shifts supply, A, is P sub H. Answer. 1. Solve for the equilibrium price of processed pork in terms of the price of hogs. To obtain an expression for the equilibrium similar to equation 2.14, we equate the right-hand side of the demand function in equation 2.3 and the supply function equation 2.6 to obtain 286 minus 20p equals 178 plus 40p minus 60 p sub h, or p equals 1.8 plus p sub h. Equation 2.17. As a check, when p sub h equals its typical value, $1.50, the equilibrium price of pork is P equals $3.30 according to equation 2.17, which is consistent with our earlier calculations. 2. Use this equilibrium price equation to show how the equilibrium price changes as the price of hogs changes. Differentiating the equilibrium price equation 2.17 with respect to P sub h gives an expression of the form of equation 2.16. dP over dP sub h equals 1, equation 2.18. That is, as the price of hogs increases by 1 cent, the equilibrium price of pork increases by 1 cent. Because this condition holds for any value of P sub h, it also holds for larger changes in the price of hogs. Thus, a 25-cent increase in the price of hogs causes a 25-cent increase in the equilibrium price of pork. 3. Write the pork demand function as in equation 2.15 and then differentiate it with respect to the price of hogs to show how the equilibrium quantity of pork varies with the price of hogs. From the pork demand function equation 2.3, we can write the quantity demanded as capital Q equals capital D of P sub H equals 286 minus 20P of P sub H. Differentiating this expression with respect to P sub H using the chain rule, we obtain an expression in the form of equation 2.16 with respect to P sub H. D capital Q over dP sub H equals D capital D over dP multiplied by dP over dP sub H equals negative 20 times 1 equals negative 20. Equation 2.19. That is, as the price of hog increases by $1, the equilibrium quantity of processed pork falls by 20 units.